Trevor Beach.
Good evening, everyone. I'm Trevor Beach, and I will be talking about black hole thermodynamics. To give a brief overview of my presentation, I will be basically defining what a black hole is or what we think it is. I'll go over physical properties and the very basic structure. I will define the event horizon, I will define singularity, and I will go over the 4 thermodynamic laws of black holes, and then more or less compare them to our 4 laws of the universe. Alright, first of all, what's a black hole? No one really knows what a black hole is because obviously none of us can experience this firsthand, so all we do know is from theoretical formulation and observation. And it is currently defined as a region of space having a gravitational field so intense that no matter of radiation can escape. Alright, the physical properties and structure. Structure would be spherical, of course, and it has 4 size categories. First being supermassive, which is the size of several solar systems. Supermassive black holes are believed to be at the center of every galaxy in the universe and has a mass somewhere between 100,000 and 1 billion suns. The next would be intermediate mass, which is about the size of Earth, which has about the mass of 1,000 suns. Next would be the stellar size, which is about 30 kilometers, I should say, diameter. Anyway, 30 kilometers in diameter, and it has a mass of about 10 suns. And last is micro, which is about 1/10 of a millimeter in diameter and has the mass of our moon. There are 3 independent physical properties as defined by the no-air theorem, which is a theorem derived in classical black hole thermodynamics. And it specifies mass, angular momentum, and electromagnetic charge. Now, of course, there are other properties such as temperature and entropy and area, but those are defined in quantum mechanics, and they will be mentioned, but they aren't necessarily part of black hole thermo. The event horizon is defined as the boundary in space-time for which matter and light may only travel towards a black hole. This is the most notable feature of a black hole. This is what every picture on the internet is going to depict. And 2 theories arise out of this. One is gravitational time dilation, which is derived from the theory of relativity, which states that time passes differently in locations in space with different gravitational potentials. So to an observer, time will pass more slowly inside of a black hole. The other is the gravitational redshift, which is for an object falling into a black hole. And this is again to the observer, but it is defined this way. So for an object falling into a black hole, its physical process would slow down. And to an observer, if this object were emitting any light, the light would shift into the infrared spectrum. And of course, the light would be dimmer if it's also down. Singularity is a point in space where the curvature of space is infinite. There is supposed to be one. Lies at the center of every black hole. Singularity has 0 volume and thus infinite density. And an object falling in a rotating black hole may avoid the singularity, which gives rise to 2 theories. One being that you're going to be in a closed time loop, and so you can theoretically visit your own past. And the other would be that if you were to avoid the singularity, you would go through a wormhole and end up in some sort of alternate dimension or parallel universe, or any way you want to look at that. Hawking once argued that all matter and radiation that fell into a black hole was obliterated or sent into a parallel universe. He has since amended that. He did that sometime in the 1970s. He amended that in 2004 and said that any information lost in the black hole would then be re-emitted back into space. This radiation is called Hawking radiation. If I may try to describe this, if you were to imagine a pair of virtual particles existing at the event horizon to the border of the black hole, a negative charged particle and a positive charged particle would coexist. The negative would fall into the black hole, and the positive would be hurled out into space. This positive emission would be called radiation. The zeroth law of black hole thermodynamics states that the event horizon has constant surface gravity for a stationary black hole. The curvature of space at the event horizon is said to be constant, which makes the surface gravity constant at the horizon. This law is analogous to the zeroth law of thermodynamics, saying that the temperature of a body at thermal equilibrium is constant. The first law, which is almost exactly the same as ours, is the conservation of energy. This is the equation. N being the mass, A being the surface gravity, A being the event horizon area, we have angular velocity, angular momentum, V is electrostatic potential, and Q is electric charge. The second law states that the event horizon is a non-decreasing function of time. The change in area is greater than or equal to zero, in other words. This is analogous to the second law of thermo, which is the change in entropy is greater than or equal to zero. Hawking proved that the area can either grow or stay the same, it can never decrease. And Jacob Bekenstein gave us this formula here, which relates entropy to area. And the third law is it is not possible to form a black hole with vanishing surface gravity. Boltzmann constant K must be equal to zero, cannot equal to zero, and this relation defines that here. T of H being the temperature at which Hawking radiation exists. And here are my references. Are there any questions?
Why does the negative particle go into the black hole and not the positive particle?
Because if the negative particle were to go out into space, there would be a particle existing in the universe with a negative charge, and that, I mean, according to what I read, is not possible.
How do you find a micro black hole?
That is something we actually create. They can't really find any of these except for absences of spaces in space, like absence of where light should be. And the micro is something we fire protons together to create micro black holes in the planet. That was actually a big controversy like a few years ago, that they thought the Earth would be destroyed if it got out of hand. Anyways.
And like, what kind of black hole is nearest to the Earth?
Nearest to the Earth?
Yeah.
I have no idea. I mean, it could be, but I guess the most common.
Somewhere.
Yeah, most common would probably be intermediate mass, since that would be the most likely size of one to exist closest to us. If not that one, would be the supermassive black hole in the center of the Milky Way.
What molecule is one dimensional black hole? Is that logical?
Supermassive.
Is that what?
Yes.
Is that logical?
Is that logical?
Yeah.
I mean, we exist, so obviously not. It may be a micro.
I'll be
It
sure
doesn't have the mass of the moon.
I'll be sure and share.